This is Bill Farmer again with McMaster University course Computing and Software 701, Logic and Discrete Mathematics. We are looking at a series of topics under recursion and induction, and today we're going to look and compare weak induction with strong induction. Now, first we want to talk about something very important idea called strengthening the induction hypothesis. So sometimes when you're trying to prove a statement, you can't prove the statement by induction because the resulting induction hypothesis is too weak. The hypothesis does not have enough information to allow us to do a proof by induction. So there's a strategy called strengthening the induction hypothesis. The idea here is to prove a stronger statement. And by proving the stronger statement, we're going to get a stronger induction hypothesis, which will enable our proof by induction to work. So I'm going to just briefly describe an example of this. It's a very simple example. There's a theorem that says every square number is the sum of two triangle numbers. So let me just show you what I mean by that. So a triangle number is a number like this that we represent in a triangle, or a number like this. So this is 3, this is 6, those are triangle numbers. And of course a square number is a number we represent like this. We can put in a square. Now, if we look at a square number like this, so this is square number 16. Now what I can do is, if I collect up this part right here, that is obviously a triangle number. So that's 10. And then this part here is also a triangle number. That's 6. And we know 6 plus 10 equals 16. So the theorem says, and it's pretty clear just from this picture, that any square number is going to be the sum of two triangle numbers. Okay, so that's the theorem. But if you try to prove this theorem, you can't prove it by the induction. It's because the induction hypothesis is too weak. But we can prove a stronger statement, and that stronger statement is every square number is the sum of two consecutive triangle numbers. If we prove that statement, then we get a stronger induction hypothesis, and our proof by induction will work. So if we go back here, we will see that 6 and 10 are actually, they're both triangle numbers, but they are consecutive triangle numbers, because we get to 10 by adding the next row. Okay, so that's the idea of strengthening the induction hypothesis. So let's now go on to thinking about weak induction versus strong induction. So I mentioned earlier that weak induction is basically structural induction for the natural numbers, and strong induction is ordinal induction for the natural numbers. And we get two induction principles, and these principles look different, but they are actually equivalent. Let me just jump to the next thing. There's a theorem that says weak induction and strong induction are equivalent. They're equally strong. anything we can prove with weak induction, we can prove the same in a similar way with strong induction. Now, with weak induction we have we're trying to prove this. Same way we're trying to prove this. We're trying to prove a property holds for all natural numbers. We first show the property holds for 0, and then we show whenever it holds for x, it will then hold for the successor x. That's what we have to show. With strong induction, it's different. We're going to show that for any x, whenever the property holds for all y less than x, then it will hold for x. If we can show that, then we know it holds for all x. So when we're doing a proof by weak induction, we start with the base case. We show that p of 0 holds. Then we assume p of x. And then we show that p of s of x holds. Now, it's a little different for strong induction. We let x equal 0, and then we show p of x. And then we let x be greater than 0, and then we show p of y for all y less than x. Okay, so the last thing I want to mention is, why is strong induction called strong induction? It's called strong induction because it gives a stronger induction hypothesis. So let's go back and see why that's true. So here, if on the induction step, we're trying to prove this fact, and we can use this fact. So we're trying to prove the successor x, and we can use the property holds for the x just smaller than the successor of x. But here, it's different. Here, we're trying to show p of x, and you might think, well, if we change our language a little, up here, if we're using this approach, all we can assume is p of x minus 1. But we can actually assume p of y for all y less than x. So this is definitely a stronger induction hypothesis. Okay, so that will end this presentation. And next time we're going to talk about recursive, or I should say primitive functions and general recursive functions. So thank you very much.